Good morning, guys.
Morning.
Okay. Okay, guys. Now, any questions so far? Yes, guys. Any questions about your artifacts?
No.
Doppler? Okay, guys. Now, the other day we got stuck at enhancement because the anatomy getting flipped upside down. Okay, that's good. Let's see, guys. So, did you guys get what enhancement was? Okay. Now, first of all, you're going to be is going to appear as hyperechoic. Clear? Okay. And we can mean it says, okay, the reason for enhancement was due to a low attenuating structure in the beam's main axis. And these hyperechoic reflections that are going to be, I guess it's okay, deeper to the low attenuating structure. Okay. Now, unlike your shadowing, it was just that, okay, as the reflections that we get are going to be overly bright. Okay. So you can mainly say, okay, if you look back in our assumptions that should be violated, we can mainly say that the last assumption has been violated here. That the strength of the reflection related to the characteristic of the tissue creating the reflection. That is not the case here. Here, the strength of the reflection is stronger than the reflection created by the tissue. Yeah, okay. Did that make sense? And that's why it's okay there. That's why we call it enhancement, and they're going to become hyperechoic. Did you guys get that?
Yes.
Good. Yeah. Any questions? Okay. So one thing to remember is that, okay, yes, enhancement mainly is okay, is going to be hyperechoic. Now the next, okay, the subtype of enhancement that we may have is what we may call focal enhancement. Yeah, okay. Now focal enhancement, yes, okay, can also be called focal banding. So another name for your focal enhancement is going to be focal banding. Now just look at it in this way. That's probably going to be okay, an easiest way to look at it. Now when we said enhancement, what was that going to be? This is going to be okay, a hyperechoic reflection. Is that clear? Okay. But the question is, where is it that this is going to appear? Now, if you look at the word focal, focus, and we can say it's okay, L is just our favorite, yes, okay, percentage. Okay. So, what is it your focal enhancement is going to be? An enhancement. And what is going to be an enhancement is okay, a hyper echoic reflection. Where? Yes, okay, at your focal point. Did you guys get that?
Yes.
Okay. Now, some of you may ask, or may say, okay, why at the focal point? Why may we have an enhancement at the focal point? Now, if you look at, we can say, it's okay, the physics of the focal point. What was it that I said back then? That, okay, yes, that's going to be the area in the beam with the highest intensity. Did that make sense? So mainly because of, okay, yes, the highest intensity, that's going to, we can say, it's okay, that's why it's okay that you will have a increased intensity of just, okay, the reflections produced at this point here. Now, can anybody tell me why is it that at the focal point or at the focus, is it that a beam will have its highest intensity? What was the whole idea behind that?
The area is the smallest.
Exactly, that's the point of the beam where the area or the diameter of the beam is smallest. Okay, so all that energy mainly is, okay, you can say, okay, squeezed into a smaller area, mainly causes the energy to be higher. Clear? Okay. And reflections, that's okay, produced at that point maybe, we can say, I'm sorry, overly bright. Okay, guys? Now, there is one way in which we can, let's say it this way. I may say it's okay, how can we fake a focal enhancement? And what I mainly as okay mean by faking here is that we actually as okay wouldn't have had a focal enhancement, but we actually is okay may be able to produce something that looks like focal enhancement. Okay. Because mainly as okay, just doing the step opposite to faking the focal enhancement can actually as okay be a way by which you may as okay get rid of the focal enhancement. So the step opposite of faking it is mainly as okay because it is okay the step to get rid of it. Let's say this is our image. And let's just say that, okay, yes, we did something to, this is a faked focal enhancement. It's not a real focal enhancement. We mean, yes, okay, just produce this by doing something on our system. Is there anybody who will be able to tell me what they think that we did to fake the focal enhancement or produce a fake focal enhancement?
You have incorrect time gain compensation.
Amelia?
You have incorrect time gain compensation settings.
Yes, Kristen. But would you like to elaborate? Your answer is right. But would you like to elaborate the term incorrect?
So if you have it too high in shallow
Exactly. If
depths.
you fakely have, for instance, okay, increased the time gain compensation at this point here, what would that do? That would mainly cause that, okay, as the intensity of the reflections that were reflected from this depth here got falsely overcompensated. And that's why it's okay, you have this. Okay, so it's okay. If you see as okay a focal enhancement, what will be a step to correct it? Or we can say, okay, get rid of it. Okay, is mainly as okay by reducing the time in compensation at this depth here. Did you guys get that?
Yeah.
Okay, guys. Now another question. Another question that I have. Let's say that, okay, yes, we haven't overdone our okay time gain compensation. And let's say it's okay that we see it's okay a bright strip here. Okay. This is hyperechoic. This is hyperechoic. Clear? Okay. Now there's nothing wrong of seeing yes okay something yes okay like this across your screen. It could have been yes okay a structure which was a bright reflector. Clear? Okay. But how would you be able to say that okay at this hyperechoic strap here across the screen or horizontally across the screen is or is not focal enhancement? Let me ask you, yes, okay, how would you be able to say, okay, this is mainly, yes, okay, due to a focal enhancement? Yes, guys. Yes. Anybody? Yes, guys. Nobody even want to guess? Okay, guy, let me, sorry. Where is it that a focal enhancement is going to appear?
At the focus.
At the focal point, right? Okay. Clear? Okay. So if you see as okay, this band here, like this, at your focal point, you're gonna say, well, okay, this is nothing but it's just a focal enhancement. Did that make sense?
Yeah.
Good. Now is my next question then. That we say it's okay if you say that this here is your focal point, but how on your system would you know that this is your focal point?
Is it the banding?
No.
Because there's a marker where the focal
There's a
point-
marker, right? Okay, so usually that's okay. At your focal point, you may see it's okay. Now some systems have that. Hourglass appearance, some systems, yes, okay, mainly yes, okay, just have a arrowhead. That way mainly is okay, mark that this is your focal point. Did that make sense? Did that make sense? So if you see that your focal point, that's okay. What would that mean? That, okay, yes, it is a focal enhancement. Clear? Did that make sense?
Yeah.
Good.
Yeah.
Now what? Okay, now how you want to make sure that, okay, yes, it is a focal enhancement or isn't? Or is, okay, is this really, or is this not a focal enhancement, but actually it's okay, a hyperechoic structure? What can you do? Scooby-Doo, what can we do?
You change the location of your focal point.
Exactly. So you can either move the focal point up here. For instance, if you want to, yes, okay, you can move it down here. Clear, okay? If it moves up here, for instance, yes, okay, if you moved it, the focal point, or it's okay if it appears down here, then it's okay, you can say, well, okay, it still appears, okay, where my focal point is, then it is a focal enhancement. But if you move your focal point up here, for instance, let's say it's okay, this depth, and this hyperechoic reflection still appears at this point, or for that, say, as okay, if you move it down like this, okay, and instead of, yes, okay, moving down, yes, okay, you still have your focal enhancement up here. This hyperechoic reflection up here, then it is not a focal enhancement. It is mainly, as okay, just a tissue here that's okay that produced a bright reflection. Did that make sense? Because where was it that you are going to have a focal enhancement? At your focal point. That's why we call it focal enhancement. Okay, what was going to appear at the focal point? An enhancement. What was that enhancement? A hyperechoic reflection. Clear? Okay, not necessarily as okay produced by a tissue at that point or at that depth, mainly as okay just an artifact due to the focal point, the increased intensity of the focal point. Did that make sense? Okay, so if it still stays there, even though, yes, okay, you move your focal point up or down to shallower depth or deeper depth, how would that make it? Well, okay, that's how you may be able to say, well, okay, this is not an artifact of focal enhancement. Because if it was, then it would have moved with you changing the focal point. But if it moves as you move your focal point to shallower depth or deeper depth, then it is an artifact called a focal enhancement. Did that make any sense? Okay. Now, guys, yes, okay, these things are not written in the book. Or are they? Are they written in the book? If you look at focal enhancement, was this thing written in the book? I guess not. Clear? Okay. This is what you're saying, yes, okay, thinking outside the book, or yes, okay, you can say read between the lines. Now, how do we establish things like this? By concept. So if you have, okay, it's a good grasp on the basic concept, then you can answer any question. Okay. Kristen, haven't seen a focal SOK enhancement yet. Right, okay. Or have you? Have you seen a focal? No. Right, okay. So you haven't seen it yet. But it's okay if you just look at the definition, look at the concept that caused it, so and so. That's how it's okay. Even as okay, if something wasn't mentioned in the book by us, okay, you just use your gray matter, then yes, okay, you'll be able to figure something out. Okay. So one thing about artifacts, or what you may as okay see as artifacts. If it's fake, if it's something that is caused by us, okay, you can say it's okay, the beam and so on, so on, so on. Okay, which is not accurate. It will disappear once you start as okay maneuvering or changing around with. That's okay, either you're setting or the direction from which you are scanning and so on. So, whereas if it wasn't an artifact, but it's okay, an actual it's okay structure, it will stay there. Okay, it won't go anywhere. Clear? Okay. Did you guys get that? Okay. Now, practically, yes, okay, whether it was a structure at this depth here, that means, yes, okay, it just was super, yes, okay, overly bright. You may just reduce the brightness of it. Whether it was due to, yes, okay, focal enhancement, because this was your focal point, or the other way around, but you can always, that's okay, reduce your TGC, and it may, as okay, make it, we can say, as okay, slightly darker, or reduce its brightness. Any questions? Right, okay. Well, that's okay, as we said earlier. Well, that's okay. How to fake it, or it's okay, fakely produce, that's okay, something that may mimic or look like a hyper echoic reflection across or horizontally across your scan. Could mainly is okay by increasing the TGC at the depth. So guys, verbally, how would you define, yes, okay, what the hell do you call it? Focal enhancement is going to be, yes, okay, a horizontal hyperechoic band or strip across the scan at your focal point. Any questions?
No?
Good. Okay, guys. Now, probably that's okay. One of the interesting artifact is going to be mirror imaging. Okay, and mirror imaging, that's mainly as okay, going to be as okay, we can say as okay, a kind of artifact that leads to, or we can say as okay, duplication of a structure. And what do I mean by duplication? We can mean it as okay that a second reflection is produced. Okay, is that clear? Now, guys, if you for instance, okay, take an image. And we mainly say that, okay, yes, you have a structure here. So let's say that this one here is okay, that is the real structure. And what do we mean by being real is okay, that it is physically present. Did you guys get that? Clear? Okay. So there's nothing wrong with seeing this fellow here because he or she is real. The problem is going to arise if we see as okay, this artifact here, which we as okay call a mirror image. And was it that the mirror image is going to be, that's going to be a duplication of the structure. They are duplicate, which will be referred to as the mirror image, will appear here. So this is the duplicator, this is our artifact. And what do we call this artifact? We call it a mirror image. Did you guys get that?
Yeah.
Now you may say, well, okay, wasn't that the same as okay as reverberation? That we say it's okay. This here is okay, was real. And then we just deeper down had the artifact. Okay, in which because okay, which called reverberation. No. And there's going to be okay some explanations for that. Because in this case, it's okay, this real structure here. This one was okay, the one that was a strong reflector. That then ended up as okay, producing these it's okay. Artifacts here, which what I mean is okay because it's okay, just repetition of is okay, our real structure be repeated just at an increasing depth. Okay. Now for us to call is okay, this artifact here, to call it a mirror image. What is it we will need? But we can actually say, okay, this artifact here is the mirror image of this real structure here. Okay, but the reason that we call it a mirror image is because we need something that is going to act as a mirror. Yeah, okay. And what is this structure here that's going to act as a mirror? What is that going to be? That's going to be as okay, a strong reflector. Did you guys get that?
Yes.
Good. Now, as I said the other day before adjourning the class was, please make sure that you look yourselves in the mirror. Now, what do you see when you look in the mirror?
Your reflection.
You see yes, okay, you see your own reflection, but what does that reflection looks like? Like somebody looking just exactly like you is standing at the other side of that mirror, right? Did that make sense? Okay, so in this case here, it's okay, what is it that we have? We have you as a real structure. Okay, okay. But for you to be able to see as okay, a true copy of yourself, you need a mirror. Only then will you be able to see a mirror image of yourself, right? Did that make sense? So likewise here is okay, we will also need a structure that is going to act as a mirror. Now, what is it a mirror is? When you look at the mirror, what do you see? Please don't say I see a copy of myself or my own reflection. If you look at the makeup of a mirror, let's put it that way.
Glass.
Okay. So is the windows or the glass in the windows also glass, right? Okay. You may say, well, I can still see my reflection there. Well, okay. There's some, okay, that's strange explanation for that. But what causes this, okay, a mirror to give you the reflection? That silver-like film that it has, that is the real reflector. Did that make sense? Clear? Okay. But here you can mainly say, okay, this artifact is only going to appear if and if and if you have a mirror. Yeah, okay. Okay. And why do we call it a mirror? Mainly it's okay because it acts like a mirror. It's going to be okay, a tissue that acts like a mirror. And what is it a mirror is? It's mainly it's okay, just a medium that creates a reflection. Did you guys get that? Clear? Okay. So what we will need to have is, that's okay, a tissue here deeper to your real structure. That is going to be as okay a mirror, which may or mean that okay it will be a strong reflector. Did you guys get that?
Yeah.
Good. Now that is just assume. Okay, let's just make it this way here. And say, okay, yes, we have a structure here. This blue one here is okay, he is real. Even though, yes, okay, we have a mirror, a strong reflector. Now, what we may see here, I'm just going to do it this way. Something like this. Now, let me just put it this way. Only one of the four of these circles here is a mirror image. And even if we label them, let's say as okay, A, B, C, and D. Now my question is, which one do you think is the mirror image? It doesn't hurt to guess wrong. Well, here is okay if it was like this. Only one of these here will be true, or will be a mirror image, which may mean it will be a copy of this one here. Where the remaining three of them could be or would be as okay physically present. Or we could say, okay, one of them will be physically present, and the other one, yes, okay, will just could also be just okay as a mirror image of something else, of one of the structures. So looking at these three here, four here, which do you think is the real mirror image, and which will not be?
A.
You think A is the real one? Okay. Why?
It's kind of like equal and opposite of the mirror reflector.
Exactly. So you can maybe say that the distance between this and the mirror and this and the mirror is the same. And why is that? Because, okay, guys, if you're standing in front of the mirror, let's say it's okay, you're standing really close to the mirror, your mirror image is going to appear like, okay, your mirror image is also standing close to the mirror. Whereas, of course, if you step backwards, it's just going to look like your reflection also step backwards. Did you guys get that? So that's why I mean, yes, okay, should be able to say that, okay, yes, Why? Because it's okay, the distance between the real and the mirror is going to be as okay equal to the distance between the artifact and the mirror. Did you guys get that?
Yeah.
Okay, but please keep in mind here, guys, that in mirror imaging, yes, okay, the mirror image or the artifact is always going to be deeper than the mirror, where, okay, it's the real is always going to be, because it's okay at a shallower depth than the mirror. Okay. Next thing will be that, okay, the distance between the real structure and the mirror is going to be equal to the distance between the mirror image and the mirror. Did you guys get that?
Yeah.
Good. Okay. Now this was pretty much okay. We could say it's okay what your mirror image may look like on a regular B-mode image, or as your book just says, okay, grayscale image. Yeah, okay. Now, guys, in your Dopplers, that's okay. We may also have mirror image. Now, please keep in mind, guys, as I just said, that the mirror image is always going to be deeper than the mirror, and the real structure is going to be at a shallower depth. That concept of mirror image in Doppler, that's okay, applies to your color Doppler only. Now we can say it's okay. We have the image. Let's say it's okay. We have our a little bit too far out. Okay. Now, guys, this here is your blood vessel. Now, as we already said, that okay, yes, it's only going to be as okay in the window or in the box that is going to be filled with color. Did that make sense? Or what you mean is, okay, may see deeper here. Is going to be this, where you can, it's okay, clearly see it, okay, this here. This here is, okay, was the physical outline of your blood vessel. Clear, okay. So what is it that what is it this is going to be? This is going to be, it's okay, your mirror image. And what you may see is, okay, as here, what's going to be is, okay, a bright reflector. So you can actually say that, okay, in this case, is okay, this bottom, or is okay, deeper wall of the blood vessel. Acted or acts like the mirror. And that's why it's okay. Deeper to it is okay. This here is okay, was your mirror image. You guys get that?
Yeah.
Okay. So even in color Doppler, that's okay. You can say the mirror image is going to, that's okay, which is the artifact. Okay. It's still going to appear deeper than the actual blood vessel. Now, just from the color here is okay, yes, okay, in the forest, yes, okay, to our color map, we may say, yes, okay. We had let's say it's okay, a positive Doppler shift. Yep, okay. Now, guys, in what we can say is okay, the spectral Doppler. Well, okay, as what we here call mirror image will be referred to as crosstalk. Clear? Okay. Now we can say as okay that here, okay, just because okay we had, let's say it's okay, a positive Doppler shift. Okay. Now it's okay, what we have is going to be as okay, a mirror image, which is just going to be as okay, exact copy of your actual positive Doppler shift at the negative side. But it's okay, looking at this, you will not be able to, as okay, immediately say, did I have a positive Doppler shift and this here is okay was the mirror image? Or do I have a negative Doppler shift? And then this one here, for instance, okay, was my mirror image. Now I showed it the other day when we talked about it, briefly talked about it. Okay. So yes, okay. For those of you who forgot it, or missed it, here it is, a spectral Doppler. Yeah, okay. Very physically, yes, okay. If we look at this, here, for instance, like I says, okay, this is above the baseline, which is here, which we can consider as, okay, being the mirror. So that automatically means that, okay, yes, this one here is your mirror image, because that could flip upside down. That this graph actually is, okay, become below the baseline and has become above the baseline in the same person. Even if he just says, okay, he just inverted it. Okay. But how will we be able to say, as okay, child, out of these two graphs here, which is real and which is the mirror image? And that is made as, okay, determined by the brightness. So since we see that, okay, this one here is brighter than this one here, that makes this one here, sorry, the brighter one being the real Doppler shift. Where this one here is, okay, just is the mirror image or crosstalk. Did you guys get that?
Yeah.
Right, okay. So the one of the two which is going to appear brighter is going to be the real one. The one that's going to be darker is the artifact. And here is, okay, we call the artifact is, okay, a crosstalk. Okay. Had this reflection here been seen down here, the brighter one being down here and the darker one being up here, then we could say, okay, we would have had a negative Doppler shift with this. I mean, it's okay, just being as okay, looking like this, being as okay, the artifact. Did you guys get that? Okay, so it shouldn't be understood as okay, just unlike as okay or traditional mirror imaging, where it's like whatever is above the strong reflector here. Oh yes, okay. About the strong reflector, which acts as the mirror here, is the real, and whatever is below is the artifact. Okay. In this case, as a spectral Doppler, that's okay. It is going to be as okay, which of the two reflections or graphs is brighter, is real, and okay, which one is darker is fake. Did you guys get that? Okay. So for instance, students, yes, okay, you can be given this question here, or this picture here, and they can ask you a bunch of things, right? Clear? Okay, you may be asked, okay, as what is your Doppler shift? Now you may be looking at it and say, well, okay, I see something on the positive side, I see something on the negative side. Okay. And you may be wondering, okay, so which of these two here is the real Doppler shift? Okay. We can say, okay, in this case, is okay, our actual Doppler shift is positive. Okay, you may be asked, okay, yes, what artifact do you see? If any. Well, okay, yes, the artifact is going to be crosstalk. Okay, they may ask you, as okay, which of these two reflections here, or graphs here, is real or fake? Now, please keep in mind, guys, okay, they may flip the picture upside down. Clear? Okay. Mainly so, yes, okay, to check on whether, yes, okay, you know that, okay, it's always going to, yes, okay, when we see something like that, the one that is dark or less bright, which is the artifact. All crosstalk. Okay, guys. But please, yes, okay, remember that, okay, yes, in your B mode imaging, what do we need for a mirror image? You will need a mirror. And what do you get as a result of that? You get the artifact called a mirror image. Where is that going to be? Deeper to the mirror, which is going to be a strong reflector. Now, on an image, how is it that a strong reflector is going to appear? And that will be Christina who should tell me how a strong reflector will appear.
Brighter.
It will appear bright. Very good. Right. Okay. Okay. So it's going to appear bright. Okay. And then deeper to that is going to be your artifact that we call the mirror image. Okay. Okay. Now you may see as okay multiple structures deeper to the mirror or the mirror strong reflector. So the next thing that you can be asked is out of these, which of these is the real mirror image? Okay, or the actual artifact. Okay, which may mean that okay, yes, all the other structures would have been physically there. They are not artifacts. Okay, so the next that will be mainly is okay that you know that okay the distance between the real structure and the mirror or the strong reflector is going to be equal to the mirror image and the mirror. So next time you stand in front of a mirror, just step a few steps back and it looks like, okay, as your own reflection. But your true copy who stands at the other side of the mirror also steps back. So yes, okay, understanding mirror imaging is as easy as looking yourself in the mirror. Okay. It's not going to be that, okay, yes, you step back and okay, your mirror reflection steps ahead or closer to the mirror. Did that make any sense, guys? Okay. So next time you see yourself in the mirror, then you're going to look for artifacts. Okay, guys? Okay. Now in B mode, okay, in color Doppler, same concept as, okay, the artifact is going to appear deeper than the actual blood vessel. Whereas in spectral Doppler, out of the two, yes, okay, graphs, the one that is brighter is real, the one that is darker is the artifact known as crosstalk. Any questions? No questions? Okay, guys. Now just read on these two here, yes, okay, and when we come back, yes, okay, we will take a little jump to, yes, okay, somewhere later in the chapter. Because there's something that may look like a mirror artifact. Why would it look like a mirror artifact? Because it's going to be a duplication, just like mirror imaging. But it's not going to be called a mirror image. And there's one distinct or two distinguished things, yes, okay, features that's going to, yes, okay, differentiate between this new artifact, not new, but this other artifact and a mirror image. Okay, so I see you guys back at UBC 1020-ish. Is that fair enough? Okay, guys. Now, any questions about your mirror imaging? Yep. And let's just take a small step and go to page 368. And where we mainly okay, we'll talk of refraction. Now, guys, the reason that we call it refraction because this artifact is, you guys says, okay, produced or appears due to refraction. Is that clear? Okay, now what would that mean? Now, first of all, it's okay, guys. Do you recall the reasons or requirements for a refraction? Anybody?
Oblique incidence and different propagation speeds.
Exactly. So you can say it's okay, an oblique incidence and difference in the propagation speeds. Okay. So that will mainly cause that you will have a refraction of the transmitted wave or pulse. Okay. Now, what did this refraction actually mean? That there was a bend in the angle of propagation. So mainly it's okay due to this bend in the propagation violates the first assumption that says, okay, sound beam travels in straight lines because it was able to bend. Okay, that bend was what we call a refraction. Although it's okay, these were the two requirements that was to be fulfilled before a refraction, which would be a bend in the sound beam to occur. But that refraction, which is the bend caused by these two requirements to be fulfilled, produces an artifact or art refraction. Okay. Now the reason that as I take refraction, I took this step from skipping a couple of pages in the middle, is mainly because like mirror imaging, refraction as an artifact is also going to be a duplication of, let's say, the real structure. Okay, with we can mean this as two main differences. Different from mirror image. Okay, so to look at that, let's just look at first of all, what was it that a mirror image looked like? And likewise, we can say, what is it? Okay, it's a refraction would look like. Now, guys, in a mirror image, let's say this one here is real. What we have in a mirror image is going to be the mirror, which is going to be a strong reflection, which mainly mean it's going to be a bright reflection on your image. And deeper to that, is going to be your mirror image. So in a mirror image, that's okay, although it's okay, we have a duplicate of the real. Okay, but here, okay, and that's what we'll call a, okay, that's what we'll call a mirror image. Is duplicate here. Okay. Or what we can say is that this duplicate or the actual mirror image is going to be deeper to the real reflector or real structure. And what we mean is okay, and we guess it's okay in between the duplicate or mirror image and okay, yes, the real reflector or structure is a bright reflection or the mirror. Did you guys get that?
Yeah.
Good. Now in your artifact called refraction, what we need to occur is, or what needs to occur is going to be a refraction to occur. What is that going to be? It's okay, that bend in the transmission angle. Okay, which like your mirror image is going to just okay produce a duplicate. Okay, but the first thing that we need is that okay, yes, we can say that the beam or pulse needs to refract. So let's just say that this is your beam. Did that make sense? Now what is going to just okay make it refract? First, because it's okay, we can say it's okay that that's going to be it's okay a difference in speed between yes, okay, let's say it's okay, this medium here and this medium here. So these two medium here have different propagation speeds. Okay, but the next okay, yes, another thing is that okay, this beam here also got a hit a structure at an oblique angle. Okay, which mainly is okay, now we'll cause it to refract. And mainly it's okay, let's say it's okay. Here a structure here, which will be real. So we can say it's okay, we can say the refracted beam is okay. It's a structure. We can say it's okay, which will be real. So real is okay, physically present. Okay. Or what we actually will do is, because it's okay, a duplicate of the real structure. Will appear. And what do we see here? At the same depth as the real structure. Or more correctly, side by side to the real structure. So this is going to be as okay, your artifact. Because had it not been for the had the beam not being refracted. Okay, let's see how it traveled down straight here. But since it reflected, it hits a structure over here, which actually is okay, will be shown here. Or a copy of this actually is okay, will be shown here. So this becomes just okay, your artifact. Did that make sense? So now looking at these side by side, what we mean you can say is okay that we don't have in a mirror imaging. Also in a refraction is that there's no mirror. Or we can say it's okay, there's no strong reflector between your real structure and the artifact that we call a refraction. Is that clear? Another difference that we also see is that, okay, yes, in mirror imaging, is okay, the real structure is okay, was at a lesser depth, whereas, okay, as our artifact called a mirror image is at a greater depth. Did you guys get that?
Yeah.
Right, okay. And in between them, yes, okay, was the mirror. Where here is okay, it's not one being shallower and one being deeper, or one being shallower and one being deeper. The real structure and its duplicate are side by side. Okay, there we do can say as okay, it was at a shallower depth that we had a structure that caused the refraction of the beam. Okay, so had it not been for this structure here, it's okay, where this beam is okay would have refracted because it hits the structure here at an oblique angle. Why would it be an oblique angle? Because it's okay if it has a curved surface like this. Okay, because it's okay, even though it's okay here, it might have been straight. So it's okay, beams coming like this would be straight. But here is okay, the angle is oblique, it's not 90 degrees. That may cause it refracts like this, or it may refract like this. Did that make sense? Oh, sorry, no, probably won't refract like this. I mean, that's like this. Did that make sense? And pretty much okay. Pretty much okay as a structure being recorded by here. A copy of that will show up here, but at side by side and not shallow and deep. Did you guys get that? So this artifact here is okay, mainly was produced by the phenomena as a result of the phenomena that caused it. All of the phenomena that happened here was refraction. Okay, by mirror imaging, shallow and deep, refraction side by side. What do we have in a mirror image? It's okay, there gotta be a mirror in between. In refraction, it's okay, there's no mirror. But there's something that happened up here which caused the refraction. What was that? That's okay, where we studied in chapter 6. What the hell did we study in chapter 6? A whole bunch of things, right? But if you remember, yes, okay, the requirements of refraction. So that's okay, what can you be asked here? Will be an artifact produced by us, okay, beam hitting us, okay, an oblique angle and having different propagation speeds. Even if you didn't know the name of the artifact, you can name it out from the two criteria here because that's going to be a refraction that will occur. Did that make sense? Okay. So guys, what can you get as an answer option if you have a picture of a refraction? One of the options is going to be a mirror image. How you say it's okay, this is not a mirror image because you don't see a mirror. Likewise, it's okay if you get a picture of a mirror image. What can you get as an option too? Refraction. Okay, but why would you say, okay, this is not a mirror image but a refraction? Because, okay, there's no mirror. And you actually, okay, see the two structures side by side. Now, guys, please keep in mind that means that every time you see two similar structures by side, is it a must that it's going to be a refraction? No. Okay. It's not a must that it's going to be a refraction. What is that artifacts will do? They will disappear if you, or appear if you didn't have them. They may appear because, yes, okay, you change your, or you maneuver around with your transducer. Because, okay, an angle that, okay, as was a normal incidence may become oblique if you, as okay, move the transducer. Why? Because now, as okay, it if this is where it's okay, your beam goes. Okay. And yes, okay, you maneuver your transducer. Let's say you move it this way. Let's say that this point is okay. Angle goes like this. That angle now becomes oblique. And that may is okay lead to a refraction. Even if you say it's okay here, that's okay. My transducer was like this. You have the same structure, which means it's okay, it just lies in the same position. But it's okay. You switch the angle of the transducer a little bit, and okay, yes, now that beam is not going to be at a right angle. Did that make sense? At least not at this point here. It's okay. It may make a right angle. Let's say it's okay at this point here. Who knows? Any questions? Yes, guys.
No.
No questions. Okay. Okay, guys, then let's go back to where we were. And then talk about is okay, what we call speed error, or also known as a range error artifact. Yeah, okay. Now, guys, when we say speed error, yes, okay, there was an assumption talking about, yes, okay, speed of sound in soft tissue. And what was the assumption? Let's just see which assumption. There was something about the speed of soft tissue, right? Okay. But if you read on, yes, okay, assumption number 3. Sound travels in soft tissue at exactly 1,540 meters per second. That assumption is being violated here. And that's why it's okay we get something known as speed error, or also known as range error artifact. Okay, guys. Now the main two things that can happen is, because it's okay, either is the speed of sound greater than 1,540 meters per second. Oh, let's do this one, which is speed in soft tissue. Okay, so any number which was greater than 1,540 meters per second, let's just say 3,000 meters per second. Or in the other way, if we say that, okay, either is the speed sound going to be, sorry, lesser than 1,540 meters per second, which was okay as the speed in soft tissues. Oh my God, what the let's just say it's okay. It is okay. The speed was 500 meters per second. Is that clear? Now, whether it is a speed lesser than, or it's okay, greater than the speed of soft tissue, or lesser than the speed of soft tissue, that's okay. In both cases, okay, what would that lead to? Yes, okay, what we call a rare or speed error or a range error artifact. So yes, okay, we can say okay. In either cases, is there going to be a broken, let's say it's okay, outline of the structure. Okay. Now let us do it this way, guys. Because says, okay, that okay, yes. Is the speed of sound. Okay. Greater than the speed of sound in soft tissues. And we said, okay, for instance, 3,000 meters per second. Or if it was like this. Now, guys, in case now, what's going to happen is, let's say that we had a structure. Let's say, okay, physically, yes, okay, this is the shape of the structure. Let's say, okay, this is the real shape of the structure. Okay. But if this structure here, for instance, okay, had a speed of sound that was greater than that of sound tissue, that's okay, it's going to have that broken outline. So what actually is okay should appear like this. May is okay now appear. Let's say it's okay, something like this. All the because it's okay. They should have been its real shape. But that okay as that this here is okay due to that broken outline. But why? Why is it that okay, yes, this will appear at, which we actually can say is okay, will be at a shallower depth than the real. Lower boundary. Because these reflections here is okay produced here, since it travels faster, are going to is okay be reflected back to the system or to the transducer at a shorter time. And what the system mainly is okay may wrongly perceive as if this reflection here was present at a shallower depth. Did you guys get that?
Yeah.
So what we actually is okay have here is okay, what is this going to lead to? A reduce in the, sorry. It's okay, a shorter ERP or go and return time or time of flight. Clear, okay? Although physically it's okay, the sound traveled down here, but mainly because it was a faster speed, the system gets the impression of that, okay, yes, because this reflects back at a shorter time. Do you have a shorter go and return time? That's how the system actually may wrongly perceive it as it coming back from a shallower depth. Did that make sense? Okay. Whereas on the other case, on another side, same structure, but let's say it's okay if the speed of sound here was lesser than that of soft tissue. Okay. Now this may be as okay the actual shape of the structure. But it's okay, here we have a lower speed, so yes, okay. That structure, although yes, okay, physically would be like this, but actually it's okay may appear Let's say it's okay, something like this. Why? Mainly because okay, here is okay, it takes a greater time, or you have actually it's okay, have a greater PRP. Or let's say it's okay, let's just okay, go and return time. Because here the speeds of sound travels slower than that of soft tissue. And that's how it's okay, your system actually is okay, may perceive as is this reflector here. Isn't here, but it's okay, maybe it's okay at a greater depth. Okay. So even as okay, this here main is going to as okay work because it's okay that broken outline. Did you guys get that? Did you guys get that?
Yeah.
Okay. Okay. So it's mainly as okay, just going to be as okay that breach in the outline due to as okay either faster speed or slower speed. Okay. Now please keep in mind, guys, that the aquosity, which mainly over me is okay, the brightness of the reflections is not changing. Okay. So this one here is okay, all this okay may appear at a shallower depth, is going to be equal as going to have as okay the same aquosity as the real structure or as a real outline would have had. Likewise for this one here. Okay. The aquosity of is okay, this dark one here is still going to be as dark green here, is still going to be as okay the same as the real structures outline. The only thing that happens is that okay, yes, it appears at a shallower depth or it appears at a deeper depth wrongly because the actual shape of the structure might have been like this. Three of you running. One run at the speed of sound in soft tissue. One of you may run shorter or faster. One of you may run slower than the speed of sound. And you all three are giving us okay to travel to the same distance. But of course, that's okay. The person that comes back first, I may say, are you sure you traveled to the distance that I told you to? Or to the point that I told you to and came back? Because you came back too soon. And vice versa for the person who has, okay, it takes too long to come back. I'll say, maybe you missed the point. and you travel further and then came back. Okay, that's why it took you more time. Clear, okay. Did you guys get that? Okay. Now, what would be the time that it takes a sound wave to return back from a depth of 3 centimeters? What's the time that it takes a sound beam to reflect back from a depth of 3 centimeters?
39 microseconds.
39 microseconds. So you come back at, okay, yes, anything more than that, let's say, okay, 52 microseconds. The system will, yes, okay, think that you came back from a greater depth. Okay. Okay. But why would it take you more time? Mainly because in that medium, yes, okay, the sound traveled at a lower speed than that of soft tissue. Okay. Well, okay, the mark was that, let's say, it's okay, 3 centimeters. So it should have taken you 39 microseconds, but if you come back and let's say it's okay, 23 microseconds. Or 26 microseconds. Now, what would be my plus-up? You probably have to okay, return back from a shorter distance. Okay, so that's what you will call yes, okay, an error artifact or a yes, okay, error or time error. Oh, that's okay, so error range artifact, or range error artifact, sorry. Did you guys get that? But just remember this much here. That's okay, where the boundary appears to be at a shallower depth than the actual boundary is because of a faster propagation speed, or vice versa, where the boundary appears to have, it's okay, shows to be at a greater depth is mainly because of a lower propagation speed. And where both, whether it's at a shallower depth or at a deeper depth than the actual, causes that broken up or breach in the outline or a broken outline. Did you guys get that? Clear? Okay. Okay. Now the intensity of, yes, okay, this reflection here is not going to be stronger or weaker than what would have been produced by this boundary here. Like right here, the intensity of this, okay, your artifact, although it's okay, may appear slightly deeper, is not going to be stronger or weaker than the actual reflection which will have been produced by the boundary itself. Okay. Likewise, okay, you're not going to have 3-4 reflections here or 3-4 reflections here. X fake number of okay as lower or greater number of reflectors appearing, or likewise here. One boundary is just going to just, okay, produce one reflection. Any questions, dear students?
No. Do you recall that fellow? Lobes. Now, what was lobes? Energy like leaking, I guess, from the beam's main axis.
Okay, you can say it's okay, energy that may, that's okay, leak, escape, whatever you want. Okay. From the outer portions of the beam. Clear? Okay, okay. Or beams in main axis, yes, okay. So guys, this was our transducer. We can see, oopsie, oopsie. These here are your beams, or your beam. Now, one kind of transducer that we have lobes in far zone. Is that clear? Now, guys, for instance, okay, if this here is okay, was your image. How would you be able to say it's okay, what is going to be your far zone in your image?
The deeper portion,
Okay,
or after the focus, you see the little focal points.
exactly. So if you said that, for instance, okay, this here was your focal point, right? Okay, then we can mean it says, okay, anything beyond that focal point here, that will be the far zone. Okay, and okay, yes, what we saw in this far zone here is okay, would be the loops. When is that? Or how? Or why? Is it that we see loops in the far zone? When or why? Is the reason for it that? Why would you only see loops in the far zone? Or get loops in the far zone? What did we do wrong? No, nothing. Or what did we do since we only, yes, okay, may get loops in the far zone?
Using a mechanical transducer.
Exactly. Or if I really should be as okay whole, then I may not use the word mechanical transducer. So what is a mechanical transducer? What are different ways of, yes, okay, talking about a mechanical transducer?
One PCT.
Okay, transducer with one PCT, very good, okay, good. Another way of talking about a mechanical transducer?
Manual steering of the beam and only one focal point.
Exactly. Here you go. Good job, Caitlin. Okay. Okay. So if you're able to, yes, okay, okay. So in those kinds of transducer, that's why you have, well, okay, because it's okay, the likelihood of production of loops is going to be, yes, okay, in the far zone. Okay. Now the other kind of loops that we might get, this is what we call side loops, right? Oh, let's do it this way. These are the side loops. The other kind of loop that we got, let me say, is okay, we still have a beam. But it's okay, here it's okay. The loops that we would get are going to be all over in both near and far zone. And that was going to be as okay what we call the grading loops. Clear? Okay. And when do we get that? Or what did we do? Now, Caitlin, you don't say anything. Let somebody else answer. And let me pick my target. Yes, Angie. When and why do we get grading loops? When,
I don't-
yes,
I don't know.
you don't know.
No.
Anybody who knows? When would we get grading loops? Or what did we do since we got grading loops? Yes, Dr. Lillian, would you be able to tell us?
I know they're created with or by array transducers.
Here we go. That's all. That was all. That was what I was looking for. Okay. Okay. Because you're using SOK array transducer. Now, what would be another way of talking about array transducers?
Multifocus.
Multifocal. Okay, good. What's another thing that causes a transducer to become an array transducer? Or what enables it to SOK focus at multiple points? Now here's okay, your focal is or focusing is electronic, but how is that possible?
Multiple crystals.
Multiple crystals or active elements or PCTs. Did that make sense? Okay, so that's when you get grading loops. Okay, and where do they appear? Yes, okay, that can be yes, okay, all over the image. Of course, yes, okay, this is going to be yes, okay, a pain, and that's why yes, okay, we have mechanisms such as subdicing. Okay, we had mechanisms such as apodization. Now, is there anybody who wants to tell me what the apodization is? Yes, guys. What in the hell was apodization?
Doesn't it help to reduce side lobes?
Okay, I will more go for yes, okay, grading loops. Okay, it was a mechanism to yes, okay, reduce loops. Let's just put it this way. Good. But what was it? Or would you, in one sentence or two sentences, tell me what apodization is?
When you have your peak intensity at the center of the sound beam and then weaker intensities toward the edges.
Exactly. Where you have the strongest signal of your beam in the center. And it just gradually, okay, weakens as you get out. I go from the center towards the periphery. That was what we call apodization. Did you guys get that? Right? So those were mainly as okay. We also says okay, as dynamic aperture. Those are mean yes, okay. Mechanisms by which we yes, okay, mean yes, okay, try to yes, okay, reduce the loops from occurring or being produced. That's why you want to. Because no matter what kind of loops we are talking about, whether that was side loops or whether they were grating loops, one thing that they both have in common is that they reduce or degrade the lateral resolution. Did you guys get that? And why would that be? Now just look at it, guys. Let's say it's okay. Let's see about your image. Clear? Now let's just say that, okay, yes, for instance, this here. In this case, yes, okay, this is the beam's main axis. Did that make sense? Okay, so what would a good axial, what would a good lateral resolution be in this case here? That structures that, let's just choose a topic color. That structures that, okay, yes, appears here in the beam's main axis physically were only present in this area here, right? Did you guys get that?
Yes.
Okay, so this what I mean is okay because it's okay that there would be a case of okay a good lateral resolution. Now let's just say that okay, yes, the same thing here. Let's say okay that if our beam in this frame here was like this. Okay, which you mainly can say is okay, the structures that appear here should ideally less okay just only appear here. But yes, okay, in this case, let's say that okay, yes, we produced loops. Let's say it's okay that we have loops like this. For instance, right? Okay. Now what's going to happen is, let's say it's okay that a structure that physically is okay was here. Physically here. Actually, yes, okay, as a result of what we actually will end up calling, yes, okay, a lobe artifact. This structure will actually is okay physically appear here. Now this is going to be as okay a lobe artifact. Okay, you can even say that okay, yes, what if we had a structure which physically is okay here at this point? Well, okay, guys, there were also yes, okay, had appear here, and were also being as okay a lobe artifact. So what is that you can see is, okay, you end up with, okay, yes. This is going to be, as okay, that something which physically is here appears here. Something which physically here is, okay, appears here in along the beam main axis. Is due to poor lateral resolution. What's going to is, you can say, okay, degrade your lateral resolution. Clear? Okay. Mainly because we can say, okay, yes, okay, if it was the same thing, that's okay, yes, that this beam, of course, that's okay, will be steered here. And okay, yes, hits the structure, which we had over here, which physically was here, is going to appear here and not here. Did you guys get that? Or likewise, okay, as when our beam is okay goes this way, we can still say as okay that the structure that we said okay as physically was here is going to physically appear here, and it will not appear here. Because the reason that okay as in this structure physically is okay if it was here, appears here, and this being here is okay appears here, was because of the loops. Did you guys get that? Have you guys ever figured, yes, okay, how somebody with double vision may see things? Okay, what may cause double vision?
Dizziness.
Ah, okay. But hopefully that's okay, that's going to be temporary. What if it is permanent? What do you call that? Never heard of it? Never seen somebody with a squint? Good. And what is that they may see? Well, physically, it's okay, you'll be standing here. But they may see you as over here as well, right? Because they see two copies of you. If that makes sense. But of course, that's okay. They would know from experience as okay which of the two is real and which is fake. But if it means that okay, something which physically here is okay appears here, or physically here it appears here. In case of this, okay, our ultrasound is going to be as okay as a result of lobe artifacts. Which degrades your lateral resolution. Why do we call lateral resolution lateral resolution? It's in the word lateral. Yes, guys. Anybody want to say something? Please don't be quiet. You only got 11 more days left for this.
The ability to distinguish structures or side by side.
Side by side. Okay. So the reason that, okay, yes, this is going to be as okay, a poor lateral resolution because something which was here is here. On your image, oh my God. Something is okay, which physically is okay was here, if you see it here, is poor LR. Or likewise, it's okay. If this thing is okay, which was here, it appears here. It's again as okay. Poor lateral resolution. Okay. What caused it just okay, this to appear here or this to appear here? Well, meaning because okay, these reflections here are picked up by the loops produced by the beam and perceived as to be as okay in the wrong position. But we can say, okay, an example of this kind here is okay. If this okay as was our focal point, or mainly as okay, just being as okay, basically side loops. Because side loops are only in the bar zone. And that was mainly as okay when we used a single PCT transducer. Whereas, okay, we had loops all over, okay, which are going to be as okay, irrespective of the focal point, as okay. We could have a structure here, as okay, in this plate here. But as okay, loops that were produced all over was what we call gradient loops. Okay. But that's okay. The system has mechanisms to, yes, okay, minimize the production of loops. So lobed artifacts degrade your lateral resolution. Okay. Did that make sense? Good. Okay, guys. Now, if you just go to page 370. Now, do you guys remember your resolutions? Do you guys recall your exit resolution?
Yeah.
Good. Now, my first question will be, What are the acars of it? Or what is your exit resolution also can be known as? Yes, guys. Anybody want to tell me what lateral resolution also can be known as?
Longitudinal.
Longitudinal, good.
Radial. Range. There's a D and I can't remember it.
B, you can't remember it. Oh. Depth. It. What was its numerical value? What was the numerical value of your exit resolution?
Spatial pulse length divided by 2.
Good job, right here. Yeah, okay. Now please keep in mind, guys. You can say, okay, create a spatial pulse length due to either greater number of cycles per pulse or greater wavelength of the pulse will lead to, yes, okay, a greater numerical value of the exit resolution, which we will call that the resolution would be poor or the other way around. Would be good. Yeah, okay. Now when we, for instance, okay, look at let's say it's okay. We can do it this way. We can say, and that's why it's okay. I like the word depth resolution, because okay, we may have a structure here and a structure here, which okay is on your image. Physically, it's okay, might have been, let's say it's okay here and here. And when they is okay appear as two separate reflectors, this is because we had a good ER. Whereas, and why would that be? Mainly because of no, it's just the wrong colors. Sorry. Good. Why? Mainly because of a low spatial pulse length. Yeah, okay. Whereas, on the other hand, if these two reflectors here is okay would have been, we're going to say okay, a poor exit resolution. That's going to be as okay that these two reflectors here is okay. We have PS1. Mainly because okay, the system was not able to distinguish them or display and distinguish, and that's mainly because that we had a gray spatial pulse line. Did you guys get that?
Yes.
Okay. Now, on the other hand, that's okay if we say, so what can we call this? Is going to be as okay an artifact due to this poor lateral resolution, axial resolution. Sorry here. This poor lateral resolution mainly caused that okay as these two reflectors here. So, are not going to be as okay shown as two distinct reflectors, but as one because of a poor axial resolution, lateral axial resolution, longitudinal, radial range, or depth resolution. So a poor axial resolution is going to just okay lead to artifact. Maybe actually can say okay, in this case is okay. There will be an example of okay, yes, the number of reflectors is not real. We had two reflectors, but they appear as one. Yeah, okay. Mirror imaging, refraction, and lobe artifacts, for instance, okay, was an example of it's okay where the number was still wrong. We call one appeared as two. Did you guys get that?
Yeah.
Right, okay. If you still see two reflectors, but then you see it's okay. Okay, sorry. You saw a mirror here, for instance. Okay. This is not a good axial resolution. This is actually just okay, that would be in a mirror image. Okay, where you can say, okay, then only as okay, this one here would have been real. This one here was an artifact. So how will you know that this was a mirror image? Because okay, you had a bright reflection here. Now, guys, your lateral resolution. Yeah, okay, and again, yes, okay, what we can say is okay that is okay, of course, poor lateral resolution, of course, is okay, will still lead to an artifact. Now, guys, my first question again is going to be, okay, what are the causes of a lateral resolution?
You asked for the other names, right?
Yes, my dear.
Angular azimuthal
Okay, good. I take that one. Okay, as a mutual, I know that's
and transverse.
and transverse. Clear? Okay. Now it's in the word lateral because lateral to the beam's main axis. Okay. Or transverse or perpendicular to the beam's main axis. Then a structure here and a structure here. Okay. Should appear as, okay. You can use as, okay, similar depths or similar distance. I mean, that's okay due to it's okay because that's going to be it's okay. The next thing which would be that okay, what was the numerical value of lateral resolution?
The width of the beam.
The width of the beam. Very good. Which we know. It just says okay that it's okay, it goes like this. So that's okay. If we get an image here, we can mainly say that okay, yes. This pair here of reflectors is going to be it's okay, a poor lateral resolution. Whereas, let's say this set here is going to be it's okay, a good lateral resolution. So these two reflectors here are going to appear as, let's say it's okay, two clearly distinguished reflectors. Whereas again, we can say it's okay, this one here still will be it's okay, an example of a poor reflection, a poor lateral resolution, sorry. These two reflectors here are going to be appearing as one, are not distinguished from one another. Did that make sense? But please keep in mind, guys, that okay, yes, okay, what you mainly will need is that okay, yes, the distance between two side-by-side reflectors, side-by-side reflectors, side-by-side reflectors, okay, has to be greater than the width of the beam for it to be a good lateral resolution. Okay, if the distance between the two reflectors is lesser than the width of the beam attachment to be as okay, the numerical value, then you end up with poor resolutions. Or poor lateral resolution, or angular, or azimuthal, or transverse resolutions. Did you guys get that?
Yeah.
Now, does anybody have any questions? Any questions?
No.
Okay, guys. Now let's just look at our last, yes, okay, we can say, okay, time of spatial resolution, which is elevation resolution. Okay. Is anybody who remember the nickname for this one here?
Slice thickness.
Slice thickness. Good. Yes, guys, I know it's lunchtime, so yes, okay, you may be thinking about it, okay, a bigger slice of toast. Okay, that's fine. The longer that's okay, wait time, the thicker the thicker the slice is it that you may be able to take. Okay. Now, okay. Now there's nothing new here, guys. Okay, yes, what was the numerical value for this one here? What was the numerical value of your slice thickness or elevation or resolution?
The height of the beam.
Exactly. Very good, Jim. It was going to be the height of the beam. Okay, and again, yes, okay, the same. If the numerical value was greater, and let's just say it's okay, now right now it's okay, we are looking at the beam from the side. Then we say it's okay. We have a reflector here. We have a reflector here. Let's say it's okay, we have a reflector here and here. And let's say it's okay here and here. Okay, now they're all at the same distance from one another, but what we may get as a result of our, let's say it's okay, transducer is that to begin with. Let's do it this way. Okay. That this was the height of the beam, and this one, this, okay. This part of the image here, because it's okay. As a result of this, you have a poor resolution. Likewise, for this is okay, that was going to be poor resolution. And we can say it's okay, these two here is okay. We're having good resolution. Okay. Now the main thing, okay, yes, that you guys need to remember is that okay, yes, that we can say is okay, a poor elevation or resolution. Okay, likewise, other resolution is okay, will lead to an artifact. Okay, and the artifact that we get, okay, let's put this. The artifact that we get due to poor elevation or resolution leads to, yes, okay, an artifact known as section thickness artifact. Okay. And this section thickness artifact can also be known as, and that's plain as, okay, what tells you what it is all this about. Partial volume artifact. Is that clear? Now, guys, the appearance of, okay, as this artifact here is, okay, is in this word here. Yeah, okay. Now, partial only means, okay, just means that part of will appear as if there is a volume. Or something measured in a volume, which in this case, okay, means it's going to just, okay, appear as liquid. Okay, so what is that we actually is, okay, we'll see in what you can call is, okay, a partial volume artifact, which actually is, okay, is due to a poor elevation resolution, is that a cystic structure actually is, okay, may appear as it is partially filled with liquid, which is wrong, which is fake. It may be an empty cystic structure. Just you can say, okay, a cavity or something like that. Yeah, okay, as this is, okay, what looks like fluid here is an artifact caused by poor elevation resolution. Or if you guys may, yes, okay, just says, okay. Like a mirage. Do you guys know what a mirage is?
An imaginary object.
Okay. An imaginary object. Okay. Is it something that you see or hear or feel or smell?
That you see.
You see, okay, what does a mirage look like?
Hazy, I guess.
No, my dear. Okay, it's probably been a long time since you have seen a mirage.
I've never been to the desert, stuck
Well, you
in the
don't have to go to
sand,
the desert to see a mirage, my dear.
or been dehydrated and imagining things.
Nah, well, okay. Okay, you see it in the desert. Okay, that's good. What does it look like?
A mirage is something that you imagine. It's whatever you
No,
want
it's
it to
not
be.
something, it's just a delusion of your vision.
Right, that's something that you imagine.
No. Then all fairy tales were psychopaths, if that's the case. What is it that it appears like as if there is water in the horizon? It's not because you are dehydrated. You could be as well hydrated as you possibly could be. But it's pretty much okay, as you can say, it's okay, that heat that caused that, okay, you see water in the horizon. And you don't have to go to the desert, my dear. Just try to drive on the street on a hot day. Now, you may not be necessarily dehydrated because you have your car filled with bottles of Gatorade, Poland water, or Poland spring water, Powerade, so and so. You can't be dehydrated because of sweating because, okay, your AC is blasting at full. But you will still see us, okay, a couple of miles ahead of you. It appears as if there is water on the middle of the road. You say, well, it hasn't been raining for the last XYZ amount of days. How in the hell is the road flooded or road flooded? That's a mirage. So maybe that's okay, just that effect of seeing us, okay, something that appears like water or on the horizon, that delusion of vision is what you call a mirage. Okay, guys. So yes, okay, the thicker the slice you take, the more thirsty is it that you will become. Okay, so that's the artifact that we see as a poor elevational resolution. That cystic structures. Now, I dare not ask where you find cystic structures and what they are or where they can be, because then your lunch break is gone. Once I have to clarify that one. Right? Right, Dr. O'Brien?
Right.
Okay, dear. Okay. But if those, that's okay, falsely appear to contain fluid, that can be, yes, okay, falsely, is a result of poor ER. Did you guys get that? And that's why it's called partial volume artifact. Because, okay, what you is, okay, what is it that you use to measure liquids? You measure them in terms of volumes. Mirage or no mirage? Any questions? So, Teresa, when are you planning to go to the desert?
Never. It's too hot.
Have you guys heard of the Dakar Rally?
There's
Never
car
heard of it?
rallies everywhere.
Huh?
A car rally?
No, Dakar Rally. It's called Dakar Rally. It's actually, it's okay to run cars in the desert. Which desert? What is the name of the biggest desert in the world?
Is it the Sahara?
Sahara. Okay, where is that?
Is it Egypt? Dubai? I don't know. Somewhere
Okay,
not
all
here.
right, close. At least you're in the right continent. So where's the Sahara Desert? Where is Egypt? Which continent? Okay, guys, if you guys want to see the pyramids of Gaza, which continent do you need to go to end up in Egypt?
Is it Asia?
Huh?
No. Asia?
No, not Asia, my dear.
Africa.
Africa. Okay, although it's okay, it is the northern easternmost country in Africa. But it's a little bit more towards the west. Southwest of, yes, okay, Egypt. Upper Central Africa. That's where you find the Sahara. Okay, guys. Any other questions? No, it's not a matter, okay, because, okay, they're following you in helicopters. So it's okay. If you get stuck or something, they will come and pull you out. So, okay, guys. See you guys at, should we say, and we really only got to talk about one last thing. And what would that be? Other artifact. And the other artifact that we'll be talking about is going to be, okay, curved and oblique reflectors. The rests, I think we already, yes, okay, have talked about in detailus, or mentioned us when we got, or when you did temporal resolution. Have any of you watched the very old movies? Nope. Good. That's good. So the only one left would be, yes, okay, our curved and oblique reflectors. So would it be fair enough that I see you guys back at 12? Oh, sorry, 12 is 12. You guys have to just, okay, get hydrated or rehydrated. And okay, let's check an even bigger, thicker slice. Okay. So I see you guys back at 110. Is that okay? Have fun, sir. Gee. Welcome, guys. Now, does anybody have any questions? Nope. No questions? Okay, guys. So let's just talk about, that's okay, what we can call defect sees along either curve or what made it okay will become oblique reflectors. Now, guys, the reason that we use the word oblique reflectors here is mainly because of the Then we can say, okay, there is going to be an, we can say, okay, the oblique angle between your beam and, okay, yes, the reflector. Clear? Okay. And when we talk about that, let's talk as, okay, look at, okay, as a structure that is curved. So guys, let's just say that this is a structure that we may be scanning. Clear? Did you guys get that?
Yeah.
Now, what do we see? That, okay, yes. Let me just, I should, okay. Yeah, just, okay. Take it a little bit down. So we can say it's okay, it is a curve structure. Now, guys, if we, for instance, okay, we're scanning it from, let's say, up here. Or let's just say, yes, okay, this is how it translates. What we mainly can say it's going to be occurring here is, what do we have? We have a 90-degree angle between the tissue boundary at this point here, and it's okay, your smooth angle. Did that make sense? Now that's going to just, okay, change as we, for instance, okay, get to, let's say, it's okay, this point here. Okay. So what we mainly can say is that here, okay, we can just say it's okay, just roughly speaking, it's okay. Let's say it's okay, maybe come 45 degrees. Did that make sense? Whereas if we look here, now if we look here, what is it that we see? That, okay, yes, we may say it's okay, then we may have, okay, the total of, let's say it's okay, 180 degrees. Okay, did you guys get that? Okay, now please guys think of, okay, that this structure here is, okay, throughout is the same, it's a similar structure, which mainly mean that, okay, it's built up. Oh, yes, okay, what may is okay from, let's say it's okay, the wall here is okay, and even it's okay, the wall here is going to be, it's okay, the same composition throughout. Is that clear? Did that make sense?
Yep.
Good. Okay. So ideally, yes, okay, what should have been the case? That we could say, yes, okay, the brightness of the reflection from, let's say, yes, okay, this part here should have been the same as here, which should have been the same as here. Okay, so we can mainly say that, okay, the brightness of this part should have been equal to the brightness of the reflection here, which should have been the same as, okay, yes, what we will have had here. They should have appeared of the same brightness. But that is not the case. Now, mainly in this case, yes, okay, what we're meaning is, yes, okay, this portion of our SOK structure, which we just, okay, just can label as, let's say, SOK A, will be brightest. Why? Mainly because, okay, it's a 90-degree angle. And as we knew from back in the days, that, okay, yes, a 90-degree angle is a normal incidence, which was ideal for your diagnostic imaging, right? Because, okay, what's going to happen? Everything will reflect back. Did you guys get that? So right now, yes, okay, this part of our structure is, okay, is going to appear brightest. We can mainly say, okay, this part here of what we made just, okay, call B is now going to, we can say, okay, appear dark. And when we just go to, yes, okay, the C part here is going to be darkest. Or we can mainly say, okay, in this case, as okay, that's probably going to be no reflection. Did you guys get that?
Yep.
Okay, so what is it we, yes, okay, falsely may get the impression of, although, yes, okay, this was the same structure, its build-up was the same, okay, the composition of it was the same throughout, but it may actually, yes, okay, look different from part to part to part, or from area to area to area. Did you guys get that? Which is not real, which is not actual, because ideally speaking, it's okay, it should have been evenly bright, or it should have been evenly dark. Okay. But mainly because it, okay, yes, appears with, okay, yes, different brightnesses or darknesses, if you want to go in that direction. Okay. That is an artifact. Mainly as, okay, caused because this was a oblique or curved structure. Did you guys get that? Now, how can we, for instance, yes, okay. So let's just say it's okay that this was okay as if we scan from yes, okay. We can just call this yes, okay, angle number A. Okay. Now, how will we know that, okay, this is an artifact and not something that is factual? That, okay, the composition or it's okay, the buildup, or this is a structure which, okay, has changed its buildup as it just, okay, make a curve around like this. Because we can say it's okay, if it was the same structure, let's make this a little bit more of it. Okay, and just so we know it, Yes, okay, guys. This point here is still yes, okay, what we previously called C. Okay. This point here is okay, still going to, we can say, okay, what we call B. And this is still going to be as okay, what we called E. Okay. Well, let's say it's okay that we just, for instance, okay, change the direction from which we scanned. And let's say, okay, if we now scan it from here. Now you can mainly say it's okay, what previously is okay was no reflection at all. Yes, okay. Now it's okay, make, let's say it's okay, an angle of 90 degrees, right? So what I mainly mean that now it's okay. C in this case is going to be brightest. Yeah, okay. Since B is okay, is still just okay at that. Okay, slightly is okay, oblique. So we can say okay, B instead of is still going to be as okay in the middle. It's going to be as okay, we can say dark. Where now we can say as okay, A is going to be the darkest. Okay, so you can mainly say as okay by maneuvering your transducer from as okay, what we can say is okay, 1. We're just going to label this one here as okay as 3. Okay, maneuvering it this way. That's okay. What previously is okay was darkest, now became brightest. And what previously is okay was brightest, now become darkest. Okay, so that mainly confirms, you can say yes, okay, that way, that okay, yes, this change in yes, okay, the intensity of your reflections was really not due to yes, okay, a changing composition or buildup of the structure as we went from as okay, from one area to another to another to another, but mainly as okay, just artifacts produced by us okay, an ideal angle going to not so ideal angle and not an ideal angle at all. Did you guys get that?
Yeah.
Okay. Whereas okay, we can whereas we can still say is okay. Let's just see, it's okay. This, then this, and this. Let's say that okay, yes. Let's say that okay, yes, we scan from let's see, yes, okay, this angle here. Now in this case, as okay, we can now say yes, okay. B is okay, that makes the 90-degree angle, and that's going to yes, okay, then be the brightest area. Clear, okay. Whereas what we call C is going to be just dark. And we can say it's okay. E is also just going to be just dark. For instance, if we look at that. Right. Did you guys get that? Okay, so how do we yes, okay, confirm this? Or yes, okay, I can exclude that. Okay, this is not an artifact. but it's okay. Maybe the structure is okay, changes its composition or build up as it's okay, as it curves or makes a turn. Is okay, yes. Is I dependent upon it's okay whether the brightness of the reflections change as we okay slightly maneuver the transducer to scan from different angles or not. Did you guys get that? Any questions?
I have a question real quick. Well, not even just a question, I guess to just clarify. So you can move or rotate the transducer, but you still won't have the same brightness throughout the same structure?
You can put it that way.
Okay, thank you.
Okay. Okay. So the brightness again is okay, is going to be, you can say it's okay, can be determined. Okay. I mean, okay, will be dependent upon the angle between your beam and the structure. Okay. Where a 90-degree angle, my dear, as you said, was ideal. Why is it ideal? Because okay, what comes goes directly back. Okay, where okay, you have, for instance, okay, oblique angle, just okay, some is going to just okay go back, but okay, some is going to reflect like this. Okay, and just think of okay, yes, why is it that you may just slide on top of black ice? I hope not, but that's what happens. Just okay, where it's 180 degrees, okay, that the beam comes, well, okay, just shoom, it's not going to come back, and that's okay. Now, if that changes as you say, okay, you can say, okay, maneuver your transducer. And you say, okay, maneuver the transducer in a way that, okay, yes, beams hits the same structures, but it's okay, an area which first is okay, made a 90-degree, now makes, okay, yes, makes, okay, a 30-degree, and so on, so on. The intensity of reflection may change. If that's the case, then you can mainly say, okay, those changes were mainly as okay due to the different angles between the beam and the structure, and not because the structure's composition changed. Now, when I say composition, it's okay, mainly it's okay the kind of tissues and so on, so on, so that it is built up of. Did that make sense, my dear?
Yes.
Okay. Any questions? Now, poor is okay, temporal resolution artifacts. If you guys remember your chapter 13, anything that I said is okay, lead to a poor temporal resolution, that will be a true or poor temporal resolution artifact. Okay, and what is that going to be? A staggering movement or recording of movement of a moving structure. Did you guys get that? Now, what was spatial resolution? Overall detail, or yes, okay, specifically, yes, okay, your pixels. Clear, okay, but generally speaking, yes, okay, your lateral resolution, your axial resolution, and elevation resolutions were also just okay examples of spatial resolutions. Why? Because they were all measured using a unit of distance, or it was the resolution in terms of space. Yeah, okay. Any questions? Okay. So lesser line density, what would that lead to? In terms of spatial resolution. Lesser line density. Now, what do you mean by line density, guys? Okay, what did the line mean? Or refer to? Yes, my dear.
A pulse?
Pulse, mainly is okay derived from a scan line. So lower line density or lower pulse density. Greater space between the pulses. So what do we end having? Poor spatial resolution. Okay, guys. Any questions? Any questions, guys?
No.
Good. Now, guys, I just briefly, yes, okay, I want to take you guys to the next chapter. Or you had enough? It's not the worst.
Are we not going to do the questions?
Well, we can always answer the questions either tomorrow or another day. That's fine.
Okay.
Okay. So what is quality assurance? Does anybody know what quality assurance means? It's in the word, guys. What does quality mean? Good, correct, accurate, right? Good. What does assurance means? Pertaining to assure is okay. Okay. Now, have you guys seen those cooking shows? Hell's Kitchen and things like that? Where the master chef walks in and say, this soup or sauce or gravy or whatever the hell it is that he wants to complain about tastes like whatever. How did he or she get to that conclusion? Anybody?
Like the standard
Okay,
recipe?
tested it against that. Good. Sorry.
What?
Say what you wanted to say, sorry.
I said the standard recipe. Like how it's supposed to be made.
Okay. Now, how do he know whether it was made right or not? He wasn't there. He wasn't the one who cooked it or made it, right? That's why he comes back and complains. But how would he know that that is not up to the standards?
By tasting it?
He probably had tasted it and he said, okay, shit, how am I going to sell this to my customers? Did that make sense? Okay. Now, does that mean that he's going to eat all the soup, all the gravy, all the potato, all the the passengers, okay, through the counter to get served? Then, okay, how are the customers going to be able to get their food, right? Okay. So mainly as okay, we can say, so okay, random sampling will be a way of quality assurance. Is that clear? Okay. Now, why do we want to just okay do this or perform these tasks here? Mainly to just okay assure or make sure that our systems work ideally, or let's say okay as close as ideally as possible. Right? Okay. Which mainly as okay will just make our results or as okay testing results as reliable and authentic as possible. Did you guys get that? Okay, because the machines are machines, they from time to time will or may need some finely, yes, okay, fine tuning, touch up, etc., etc. Now, Kristen can probably talk more about that because he, yes, okay, works with machines. Do they do quality assurance on the machine that you work on, Kristen?
Yeah, you have to do maintenance on them.
Exactly right. Okay. But they mainly as okay will say, okay, the components that we make on this machine here, do they match the actual measurement that we want to achieve, or are they a couple of inches off and so on, so right? Okay. Okay. So that's quality assurance. Okay, we want something which is 6 inches long, 2 inches wide, and so, right? Okay. Did that make sense? Okay. If yes, okay, you are able to just okay construct an object like that with the machine working, because okay, it's working good. If it all of a sudden yes, okay, goes from yes, okay, making things which I would have been 6 inches long, or should have been 6 to become 8 inches long, then you can okay, something is not right with the programming or something like that, right? Then it mainly will need some tuning. Did you guys get that? Okay, so it's okay, mainly it's okay from time to time to time, it's okay, check your machines or equipment up again, that's okay, the common standard. Is that clear? Now, guys, what is going to be a okay or standard in this case here? Because okay, when you scan a patient, you don't know how his or her interior or internal organs look like, right? Okay. Did that make sense? So here's okay, you will not be using a standard, or you will not be using a patient as a standard model, if you want to put it that way. You will know, yes, okay, you will be scanning something that we know what it will look like when we scan it. And how we know what it looks like when we scan it, that's mainly as okay, because that's okay, guys. If you go on to page, let's see. Which one is the common one that we use? Well, page number 230, 330, 382, sorry. Figure 21 point or 22.1. They use what they call a phantom. Okay. Now, what is it that a phantom is? It's mainly as okay, a block made out of okay, as a kind of gel. A gel that mainly as okay has pretty similar characteristics as soft tissue. The things such as okay, propagation speed and so on. So okay. But what is it that they are put into that phantom is going to be as okay, different structures. Mainly as okay, glass rods, metal rods, etc. And what they actually will be doing is okay, scanning this phantom and comparing the image on the screen to yes, okay, the image that is displayed on the phantom. And if they match, well, you have good resolutions. Or you can say, okay, your machine is okay, yes, well functioning. If it doesn't match, then it means that okay, something is wrong with the machine. There's something that needs to be sent off to the technical department and be fixed. Or you may say, well, okay, this transducer here, its exit resolution maybe is okay, half an inch off, or 2/4 of an inch off, or something like that. Did that make sense? Okay. And now, guys, so that's pretty much okay as what quality assurance is. Now, how frequently do we do this? It depends. Okay. Some places, okay, they may see us, okay, well, we do it once a month. Every month, that's okay for the first 2 or 3 hours of the day. What's going to happen is we're going to just okay be as okay checking all our machines. Mainly as okay scan them as okay using a phantom like this. Yeah, okay. Some machines may be as okay, you can say okay from the manufacturer, yes, okay, they may say, well, okay, this thing, yes, okay, needs to be scanned or okay, checked or quality assured. After there's okay, 20,000 scannings. So once there's okay, you're close to 20,000 scannings being done on that machine, it's time for it to get tuned. Or it's okay, checked. Clear, okay, if it's okay, then okay. If not, then okay, something needs to be done. Did that make sense? Good. No, dear guys. Okay, that's fine, guys. Okay. So we can no. Okay, I guess we can take these videos on probably not tomorrow. Unless I mean no, probably not. Okay, we can take them on the 15th. Okay. Now, guys, there's just one little thing in OKS, this chapter here, that I want to bring your attention to. Chapter 22, Quality Assurance, something called the dead zone. And what's the dead zone? we can mainly say, okay, now even if we look at a image, okay, a regular image. We know that, okay, this area here is, okay, if this is the transducer. So yes, okay, pretty much, okay, yes, area is, okay, close to the transducer. Let's see. This is something like this. Maybe the dead zone. Okay. And what is it that we have in the dead zone? Yes, okay, we can mainly say, okay, that, okay, the area, and if we look at it, yes, okay, which is going to be close to the transducer, or rather, yes, okay, as you may see, at shallow depths. Okay. And what's going to happen in this area, dead zone? That the accuracy is, because it's okay, poor. Is that clear? Now, Christian, do you remember the other day that you said that we scan sebaceous cysts? You remember that one?
Yeah.
Okay. And the reason that we probably, yes, okay, won't be scanning sebaceous cysts is that it falls in the dead zone. Clear? Okay. Now let's say that you, for instance, okay, want to scan something in the dead zone. Scooby-Doo, then what do we do? Let's say, yes, okay, that there was a structure in this area here that we wanted to do, scan. Clear? Okay. What we mainly, yes, okay, just do to see the structure here, we mainly, yes, okay, just cause that, okay, yes, the dead zone is outside the image, which means, yes, okay, just cause that, okay, yes, this here now is your transducer. And what is it I may do? Yes, okay, mainly, yes, okay, use a, yes, okay, bag with gel. Yeah, okay. So what happens here is, okay, this is where your dead zone is going to be. And now, yes, okay, all this, okay, this is at the shallow depth. Oh, yes, okay. Because you can make this, okay, what you may see is, okay, on your image, this is your new dead zone. And okay, this falls at a deeper depth in your image, although it is at a shallow depth as far as, okay, as in the tissues or in the depth in the patient is concerned. Okay, so this is mainly as, okay, just a way to counteract your dead zone. Did you guys get that? Okay. Now the relationship that is going to be important is that dead zone is inversely proportional to frequency of the transducer. If you guys look on the page 1, 2, 3, page 386, the 4th paragraph, the paragraph that starts with higher frequency transducers. It says, okay, if you have a higher frequency transducer, that will have a smaller dead zone, or vice versa. A lower frequency transducer has a greater dead zone. Okay, now probably that's okay. Don't come back and say, Mike, you said that, okay, yes, at 12 megahertz frequency, transducer had a dead zone of half of a centimeter. And that, okay, as a 6 megahertz frequency transducer had a dead zone of, okay, as 1 centimeter. But that's just going to say, yes, okay. Which may mean that, okay, as if you use, okay, as a high frequency transducer, you're going to have, okay, as a shallow depth, or the dead zone is going to be smaller. Whereas if you use a high frequency transducer, also a low frequency transducer, you are going to have a greater dead zone. Did you guys get that? Oh, yeah, I can show it again here. Now, guys, and that's why I said, okay, in traditional ultrasound scanning, okay, what you will see is, oh, shit, okay, so what you will see probably is, okay, tomorrow. If we, yes, okay, hopefully we'll be able to scan. No matter what image shape we get. That, okay, the shallower depth, yes, okay, that's near enough. It's just going to be, yes, okay, what do we have? Okay, maybe scan, okay, some subcutaneous tissue, maybe it's okay, some thin layer of muscles and so on. So that's it. Not even maybe just fascia and so on. So not really as okay structure. Also, okay, not really of a clinical importance as well. Unless okay, you want to scan a sebaceous cyst. Okay. Okay, but can you scan a sebaceous cyst, Kristen?
Probably not. They're usually really pretty
Well,
small.
you can now. You can. We know the trick. We just put okay as we just use okay as a bag with somehow clear fluid. A fluid with okay as with a low impedance. Okay, and keep that. Because even it's okay when you go for the thyroid, that's going to be pretty much okay right underneath your skin. You don't have very, okay. You can say, okay, you may do as okay as they did here in the picture. Place okay as a bag between the transducer and okay as the neck. Or what is that you can do? You can choose a frequency, you can choose a high frequency transducer. We just have a smaller dead zone. And if you have a smaller dead zone, it's okay, you'll still be able to just okay scan structures which are at very shallow depths with some sort of accuracy. Did that make sense? Okay, guys. So yes, okay, sorry. But maybe yes, okay, on March 15th, yes, okay, we will look at the, that's okay, 2 videos that I wanted to show you guys. Okay. So just read a little bit about this and okay. And yeah. Maybe it's okay, just page 284, 384, sorry, and 85. And okay, then that's pretty much it. So I guess I see you guys tomorrow in the school, right? Okay. Does anybody need a ride? I charge $20 a mile. Nah, that's fine. You think you'll be able to make it there? Okay. Let's see then. Well, okay. Have fun, girls and guys. Sorry. And take care. Okay, guys?
See you tomorrow.
Okay. God
Bye.
bless. Okay. Bye-bye.